Okay, so remember when we were talking about linear motion, we meant, so now we're going to talk a bit about linear motion. Linear motion شو يعني؟ Linear motion معناته when you are moving in a straight line. Okay, معناته you are going in a straight line. You start from a point and then you end at a specific point. You're going to have your initial velocity, which we usually call u, and your final velocity v. All right, and then you're going to have here your displacement or the change of distance basically. زين اللي هو يسمونه s عادة, which is basically x final minus x initial. زين so s is usually x final minus x initial. هذا يسمونه displacement. Okay, and obviously to cover this you're going to have a specific time that it takes for you to go from u to v, and at the end you're going to have something which is the acceleration, if it's there or not. If you have constant velocity you don't have any acceleration, but if it's not constant then you're going to have acceleration. Okay, so these were your basic terms when we came to linear motion. Linear motion معناتها خط سيدة starting from one point and ending at another point or at a specific place. So just a few terms to remember. For acceleration, when we're saying accelerating معناته our acceleration is positive usually, زين, and when we're saying decelerating معناته our acceleration is negative, زين. And if you remember your units, for acceleration it was in meters per second squared. For u and for v, right, it was meters per second. For distance it was in meters, so s or the x's is in meters, and then you have your time in seconds. Okay, so this was basically what we did before the midterm for linear motion. But today what do we want to talk about? We want to talk about circular motion. So what does that mean? Simply, circular motion is if you are moving in a circle. That is all it means. Sometimes they call it circular motion or angular motion. Okay, so now the difference is when you have circular motion is, let's say we are starting from this point over here and then we end up at this point over here. Okay, at this point over here. So basically you have covered this distance right here. Okay, this is your distance s, or your displacement I should say, linearly if we're looking at it from a linear perspective. This is the distance that you have covered. If we look at it from the center of the circle, the distance or the displacement that we have covered has now become an angle, usually known as theta. Okay, so now our motion is angular. This is what is meant by angular motion. In بما معناه you are moving at a specific angle. So the distance that you are traveling is going to be known as theta instead of s. Okay, and if you guys know your basic math, so let's say the radius of the circle is r. The way you can relate this s, which is just displacement in the linear, all right, لأن احنا قاعدين نتكلم عن linearly هني الموشن, or this displacement, this linear displacement over here, we are talking about it now in terms of that angle. So how can we find this angle theta? Theta here is going to be equal to s over r, or a better way to explain it is s, this is the rule of an arc. زين, الارك اللي هو بما معناته بين هالنقطتين of any circle, the rule of an arc is s is going to be equal to r theta. تمام, معناته you are just multiplying your r by the angle that you are covering. All right, so now displacement, when we're talking about it, we're not talking about linear displacement anymore. We are talking about our angular displacement when we are in circular motion. So to relate it, like I said, s is going to be equal to r theta. And we can say the exact same thing about everything else. So let's say that we have an omega. What is omega? Omega is when we are talking about velocity, but the angular velocity. So basically the rotational velocity that we have. And how can we find it? It is exactly the same idea as here. The only difference is if we divide both of these by t, okay? So what is displacement over time? Displacement over time, if you remember from linear motion, that is simply v, our velocity. Velocity is the change of position over time, or the displacement over time, is equal to, the r will not change, but theta over t, this is now your omega, or in other words, your angular velocity. So this is angular displacement, and this is angular velocity. تمام? Obviously, we are talking now in terms of when we're looking at it from the point of linear going to angular. The last thing we have is now our acceleration. All right. So let's say we do have acceleration here. This is also known as alpha. Obviously, the acceleration بيكون مدور يعني in the form of a circle. So there's a rotational acceleration. In this case now, angular acceleration, exactly the same idea as before. So if we divide by t, both sides, v over t is simply equal to acceleration. The velocity over time, or I should say average velocity over time, is acceleration. This is going to be equal to r, does not change. But now omega, or angular velocity over time, is known as alpha, which is your angular acceleration. So this is how you would be able to relate acceleration, or all of the acceleration and velocity and displacement, linearly, okay, to the angular side. So the equations, the main equations we have is, if we want to find displacement, it is equal to r theta. If we want to find v, it is equal to r omega. Or in the case of u, which color did I do u? U was red. ما عليه. Let's do it purple for now. So in the case of u, it is going to be r omega initial. U basically means initial velocity, and omega 0 means initial angular velocity. And the last one is acceleration is equal to the radius times alpha, which is your angular acceleration. So these are your very basic formulas that you need to know. One thing, like I said here, we were saying that theta over t, all right, is equal to the angular velocity. If you remember from before, here, when we wanted to find distance, all right, or if we wanted to find velocity, it was just basically the displacement over time. This is the exact same idea here. So we can also say that omega is equal to theta, or I should say the change of theta, so the displacement basically, so from here to here, all right, over time. And for acceleration, it is equal to the change of omega over time. Okay, it is basically the exact same thing. This is not A, this is alpha. Basically the same thing that we did in linear motion. So if you remember when we derived some equations for linear motion before, this is the most important thing you guys need to know over here. When we had linear, and this is angular, okay? The first equation you guys need to know, or if you remember, was the basic one, which is V is equal to U plus A times time, T, okay? The final velocity is equal to the initial velocity plus acceleration times time. This is the exact same thing in angular, but when we are talking about angular, our V is going to become angular velocity, which is omega, is equal to initial angular velocity, which is omega 0, plus acceleration, or in this case, angular acceleration, times time. Okay, it's the exact same equations that you're going to be using here. Another thing is, what was another equation? V squared minus U squared, Okay, these equations have already all been derived previously when we were doing linear, is equal to 2 times acceleration times time. Okay? Sorry, not times time. This was times distance or displacement. Again, the same idea is applied here. So instead of v squared, it's going to be omega squared minus u squared, or omega 0 squared in the case of angular, is equal to 2 times a, or in the case of angular alpha, times displacement, or in the case of angular theta, which is angular displacement. Another equation as well is displacement is equal to u times t minus, was it minus? No, it was plus half at squared. This was another way. The idea here is every time, for example, the first equation, you use it if you do not have displacement, but you have all the other things. The second equation, you would use it if you do not have time, but you have everything else. And the last one is if you do not have the final velocity, but you have everything else. Okay? Again, this can be applied here in the same exact way. So it's going to be angular displacement now is equal to our initial velocity, or I should say initial angular velocity times time, plus half angular acceleration times time squared. Okay? Now, one more equation as well. So in this case, here we had acceleration for all of them. What if we don't have acceleration? There's one more equation, which is displacement is equal to v plus u over 2, which is the average velocity, times time. This is another equation that you can use, which you do not have acceleration in it. Yani you don't need acceleration to find it. You just need to have velocity, 3 of the 4 variables that you see in front of you, basically. All right. Again, the exact same application will happen for angular. So if you notice here, everything that we have in linear, the same exact concepts are applied in angular. فبيكون equal to over 2 plus, we're going to have omega plus omega 0, which is final and initial angular velocities, times time. So these are the most important equations you guys need to know. You need to know how to apply. You're going to need to know them both in linear and in angular format, but as you can see, if you know one of them, you're going to know the other. All right? So early on, we talked about units. Okay? We talked about units in the case of linear motion. What about in angular motion? So if you remember the equation, let's do a dimensional analysis. So if you remember, when we were talking about S is equal to radius times theta. So if we put this in units form, this is displacement, which is in meters per, just meters, actually. And radius is also in meters. So what will be the dimension of this? We'll call this dimension x. All right, we don't know what the dimension is. If you notice here, the meters will cancel with each other. This is also known as, in the case of rotation, this x is also known as radians. Okay, so when we are doing all this calculation, we are going to have everything in radians instead of degrees. All right, so when we're talking about theta, we have it in 2 values. If you remember, when we're talking about an angle, we usually talk about it in degrees. But when we're talking about displacement, we usually use radians in our calculations. You can convert it into degrees by multiplying by 180 over pi, but in our case, we're not going to be ever doing that. We just need to know how to use this in the calculator. So in other words, make sure your calculator is usually, actually it wouldn't matter much, but your calculator should be in radians when solving, but it would not matter in this case. Okay, so the unit for theta is in radians. What about omega and alpha? What about omega and alpha? So we know that omega is in is equal to the change of, or the angular displacement over time. So معناتها it is going to be in radians per seconds. Therefore, omega is in radians per second. Usually it is just given as rad for radians. Same thing now for alpha. Alpha is equal to, now we know the unit of omega is radians per second divided by seconds again. So alpha is going to be in radians per second squared. All right. So these are the units that you're going to be using when we're talking about angular displacement, angular velocity, and angular acceleration. Now, one extra point is specifically for omega. So what do we mean by omega? Omega, like I said, is we have a rotation. Okay? We have a rotation. This is what angular velocity means. معناته عندنا, for example, think of this as a tire or a wheel, and it is rotating at a specific speed. زين? So that speed that's rotating at is known as omega, which is the angular velocity. Most of the time, when we're talking about angular velocity, we are talking about omega in revolutions نسيت how to spell revolution. لا هني revolutions per minute. All right, this is how we usually, or short is RPM. زين، نفس العداد اللي في السيارة معناته ايش كثر قاعدة تلف الماكينة أو البلت، نفس الفكرة اللي هو RPM. Okay, this is what is usually given in omega. But how, when we are dealing with calculations, we need to convert this into radians per second. How? So if we're talking about revolutions per minute, we are talking about how many full revolutions, which is this, is completed in 1 minute. زين؟ يعني how many times will the wheel, let's say, starting from here, how many times will it go all the way around until it reaches back to this point, making a full revolution? Okay? This is what one revolution is. One revolution is equal to 360 degrees in terms of angles. صح ولا لا? So 360 degrees is one complete full revolution. In terms of radians, this is in degrees. In terms of radians, it is equal to 2 pi radians. Okay? So one revolution is basically 2 pi radians. معناته, when you have any revolutions, you can convert it into radians by multiplying it with 2 pi. For example, let's say we have 5 revolutions per minute, right? Or just let's say 5 revolutions. Let's not talk about time. 5 revolutions is going to be equal to 5 times 2 pi radians. All right? This is how you would convert any revolutions into radians. But when we're talking about omega, we are talking about revolutions per minute. Okay, so this is for S or theta. This is for theta. And the theta is displacement or angular displacement, meaning how many times did this revolution happen over and over and over again. This is what we mean by theta. زين? So now what about if we're talking about omega? Omega هو revolutions per minute. يعني omega is revolutions per minute. What do we need to convert it into? We need to convert it into, we need to get a solution in radians per second. Okay, that is the value that we need to get. So how can we do this? Let's talk about one revolution per minute, so we have a basic understanding. So first thing we need to do is convert the revolutions into radians, and we have already saw how we can do that. We know that one revolution is equal to 2 pi radians, and I'm going to rewrite it here. So one revolution is equal to 2 pi radians. All right, so the way I usually do conversions عشان ما أخربط, one revolution, we want to cancel revolutions here, and we want to have radians instead. So I put revolutions down and radians up. كم revolution عندنا 1. How many radians? 2 pi. All right, this way revolutions will cancel with each other and we'll get 2 pi radians remaining. All right, now this is the first part. What about the second part? We need to convert it from minutes per minute, I should say, into per seconds. So we want to cancel the minutes, which will be up, because we want to cancel it with the down over here, and it will be over seconds. 1 minute obviously has 60 seconds in it. So in other words, now we can cancel the minute with minute, and we will remain with radians per second over here, which becomes this radian per second. And we are going to be having 2 pi over 60. So this is basically the conversion rate for if you want to go from revolutions per minute into radians per second. So for example, let's say we have omega is equal to 7 revolutions per minute, or RPM. This is going to be equal to 7 times 2 pi over 60 radians per second. طبعا والعكس صحيح. يعني let's say we have omega is equal to, now we have it, for example, given as 50 radians per second. To get it into RPM, we are going to do 50 divide by 2 pi over 60, or in other words, we can say that this is equal to RPM, obviously, or we can say that this is equal to 50 times 60 over 2 pi. All right, both are correct. And when you do division, it is basically multiplying with the reciprocal. RPM. So, in other words, if I want to just make a shortcut here, if we want to go from RPM to radians per second, we're going to multiply by 2 pi over 60. Tamam? And if we want to go from radians per second to RPM, we are going to multiply by 60 over 2 pi. All right. Last point, if we want to go from radians to revolutions, just revolutions, all right? So if we're talking about revolutions to radians, we're just going to multiply by 2 pi. And if we want to go from radians to revolutions, we are going to multiply or divide by 2 pi. Okay? العكس يعني. We're just basically doing the opposite. So for revolution to radians, we're multiplying. Radians to revolutions, we're going to be dividing. If it's easier for you guys, you can either have it in this form, or you can say dividing by 2 pi over 60. Whichever is easier for you guys to understand, memorize, or whatever. Okay? And this is the most important part of the theory so far when it comes to the actual acceleration and angular velocity and all of that. Now let's look at this in an application. All right. Let's actually solve some questions from the first worksheets to see how this will be applied. Any questions so far about this? Anything not clear? I'm pretty sure it's very straightforward so far. خلنا نشوف شوية أسئلة. So we have a better idea on how to solve or how to understand this. So here we have simply preliminary questions, which are convert 78 revolutions into radians. So for the first one, it's very straightforward. We are going from revolutions. So we're going from 78 revolutions, and we want to go into radians. Again, from the rule over here, we're going from revolutions into radians. All we have to do is multiply by 2 pi. So it's going to be 78 times 2 pi. And that is the answer for your first one in radians. All right. For the second one, we want to convert from radians to revolutions. So what are we going to do? We are going from radians to revolutions. So we're going to divide by 2 pi. So it's going to be 3,500 divided by 2 pi. And that's it. That's your final answer, which is going to be this, whatever it is. You can put it in the calculator, or revolutions. All right. What about 657 RPM to radians per second? Now we're talking about angular. So this was theta, this was theta. Now we're talking about omega and omega. All right, we're talking about angular velocity instead of displacement. Okay, so what are we going to do? Again, same thing. we need to see what we're going. We're going from RPM to radians per second. معناته we are going to be applying this rule, which is times 2 pi over 60. معناته بيكون 657 times 2 pi over 60, and this will be whatever the answer is in radians per second. Same thing for the last one. We're going from radians per second to RPM, meaning we're going to go 243 divided by 2 pi over 60 RPM, or up to you guys which method you want to use. You could say 243 times 60 over 2 pi. It is the exact same question, exact same relation, I should say. And then, very simple, very basic. Nothing too crazy about it. Your calculator does not need to be in radians, no, because we are not using in the calculator. The only time you need to have it in radians is if you are doing trigonometry. لأن هني ما عندكم any trigonometry, there's no requirement for radians. So when you're doing sine and cosine, this is when you have to convert into radians. Otherwise, you can just multiply, divide, all of that. All right. Could you go through linear motion quickly again? Linear motion, we're going to see some of it now while solving questions. Don't worry. All right. And I'm going to be covering basically some of it now. Let's look at an actual question now. Let's look at this one. All right. I want to make sure I finish worksheet 1 properly, because if you understand what worksheet 1 is and you have the basics down, everything after that is going to be simple and you will know how to apply very quickly. So a cam in a mechanism makes 500 revolutions. That's the first thing you're going to look at. You have 500 revolutions, right? So it is in 500 revolutions. And how much? In 2 minutes and 37 seconds. All right. So our time here is 2 minutes and 37 seconds. So it's not saying it's making 500 revolutions per minute anymore. It is talking about 2 minutes and 37 seconds. So the first thing here, before even solving this question, I need to convert this into completely minutes. How do I do that? So 2 minutes is already in minutes. 37 seconds. How do I convert this into minutes? We have minutes, seconds. 1 minute is 60 seconds, or in other words, 37 over 60. Okay? So the total amount of minutes is going to be 2 plus 37 over 60 minutes. Okay? This is your time. Your time is equal to 2 plus 37 over 60 minutes. Let me just do that calculation real quick. It is equal to 2.62 minutes. All right? This is the first thing you do before even continuing the question. You make sure you understand what this means. All right. So it's saying 500 revolutions, not per minute, in 2 minutes and 37 seconds. To simplify this now, if we have this in RPM, we will be able to solve any question. So we need to change this revolutions per minute, per 2 minutes and 37 seconds into per minute. How do we do that? Very simple. All you do is you take your revolutions, 500 revolutions, we want it per minute. So what is the minutes here? 2.62. You divide this, and then you're going to get your angular velocity, 500 divided by 2.62. You're going to get it in terms of RPM. So it's 191.08 radians, revolutions per minute. Okay, this is the first thing I'm going to do. I didn't even read the question. I don't know if this is what they want. So yeah, there you go. What is the angular velocity in revolutions per minute? All right. So this is how you would do it. Again, I repeat, what I did is I converted the time all into minutes. Then using this conversion, once I converted the time into minutes, I just divided the total revolutions over the total minutes to get it per singular minute. All right. And I got now my omega in RPM. Now they want it, part B, in radians per second. So part B, they want it in radians per second. So they want us to go from RPM to radians per second. So what do we need to do? We need to multiply by 2 pi over 60. So we're going to do 191 0.08 times 2 pi over 60. And this is going to give us times 2 pi, 20.01 radians per second. All right? And that's it. That's how you would solve such a question. Okay? I need to go a little bit fast because there are a lot of concepts I'm trying to complete, unfortunately. I will try to slow down a little bit, but try to keep up as well. Okay? And then let's look at question number 2. Okay? Let's look at question number 2. We have a flywheel that starts from rest. So when you guys are reading a question, make sure you identify everything from the very beginning. So a flywheel starts from rest. A flywheel is basically it's a type of wheel, basically. All right. And it's, in other words, it's a wheel, so we know it's going to be a rotational type of motion. And they say that it starts from rest. From rest means omega 0, or initial angular velocity, is equal to 0, similar to linear motion. All right. So it's equal to 0 radians per second, or RPM. It's the same. It's 0. And is accelerated at a rate of 2.4 radians per second. So see here, they're saying accelerated at this rate. So our alpha is equal to positive, because it's an acceleration, not a deceleration, of 2.4 radians per second squared. For how long? For 30 seconds. So our time is 30 seconds. Question 1 says determine the angular velocity reached, or in other words, final angular velocity after the time is completed, which is 30 seconds. So part A, they want us to find omega, or angular velocity. Okay? How do we do that? We use one of the equations that I've shown you earlier. And the best equation is this one, because we already have all of these givens. So when you look at the equations that I showed here for linear and these equations over here, okay, let me just copy paste these and take them as I go, so you guys can have a reference point and make them a bit smaller. All right. So these are the equations that we have. So we need to look for an equation which we have all of these givens. So we have omega 0, we have alpha, and we have t. We need to look for something where we need to find omega, and you have omega 0, alpha, and t in it. So if you notice here, the first equation is the most reasonable, because we have omega 0, we have alpha, and we have t, and we need to find our omega. So we can just apply that equation, which is omega is going to be equal to 0 plus alpha, which is 2.4, times time, which is 30 seconds. Okay, so all I did was I just applied this first equation over here. Okay, let me keep the text and let me just highlight it over here so you guys can see what I did. I used this first equation over here. All right, this is the equation I used to apply, and I just substituted in my values. So now I can find that omega is going to be equal to 2.4 times 30. So 2.4 times 30, معناتها it is 72 radians per second. All right, so make sure always your units are correct. Here, acceleration is already in radians per second squared, time is in seconds. So this will be in radians per second. This was part A. Part B. If after rotating for some time at a constant angular velocity of 72 radians per second. So معناتها it has been rotating for a very long time. So we're talking about a new case now, right? So B, we have a new case where our omega 0 is now equal to 72 radians per second. لأنه we are looking at it from a different point after it already has been rotating. So يعني the initial point of it is when it's rotating from 72 radians per second. Brakes are applied to the flywheel, producing a deceleration. Now we are talking about deceleration. All right. Deceleration meaning we are talking about a negative value. Decelerating is the opposite of accelerating. So it's minus 4 radians per second squared. Then, when we're talking about acceleration, معناته we are increasing velocity, that means it's a positive value. When we're talking about deceleration, معناته we are reducing velocity, meaning it's a negative value. Determine the time taken to reduce its angular velocity to 40 radians per second. And this is the final angular velocity that we are going to reach to, which is omega is equal to 40 radians per second. All right? If we look at our equations again over here, the most reasonable one, you could say, okay, is the same equation that we used earlier, because what are we trying to find? The time. So what do we have? We have omega 0, we have alpha, and we have omega, and we need to find time. So we are going to be using this equation, all right? The first equation over here. So we're going to be using omega is equal to, let me just plug in the numbers directly since the equation is here. 40 is equal to omega 0, which is 72, plus alpha, which is negative 4, times time, which is what we are trying to find, t. Now we just solve for t in this equation. So we're going to take the 72 to the other side. We're going to get minus 4t is equal to 72, or 40 minus 72. All right, just basic algebra, 40 minus 72, minus 4t. All right, simplifying this, we are going to divide both sides by minus 4. T is going to be equal to 40 minus 72. Obviously here the minus 4 and minus 4 will cancel. So 40 minus 72 divided by minus 4 is going to give us 8 seconds. All right. Is it clear what I did here? All I was doing was applying the equation, seeing what is the given values. If you notice, the trick here is understanding what the question wants. يعني لازم تقرون السؤال بوضوح تفهمون شو المقصود من السؤال. So it was saying after rotating for some time. معناته there was a specific amount of time that has passed on. So we are not considering everything from before this point. We are considering now our new initial point is when the flywheel is already rotating. So the initial angular velocity is going to be 72 radians per second. Brakes have been applied. معناته we know it's slowing down. So we know there's going to be a deceleration. And the value of the deceleration is 4 radians per second. So it's going to be negative 4 radians per second because it's decelerating. Determine the time. So we know we need to find time. All right. Determine the time taken to reduce its angular velocity to 40 radians per second. So this is the final velocity or angular velocity that we need to reach. And simply we just plug it into the equation in any of the equations where we have all of the givens. And then we solve for t. Okay. Let's look at the next question. Any questions about this before I move on? And then let us look at question 3. All right. So question 3 says, just a second. All right, so question 3 says, a flywheel at a constant angular velocity. Look at the word here, constant angular velocity of 150 revolutions per minute. معناته it has been going for a very long time constantly without the change of velocity. So this is our initial velocity of 150 revolutions per minute. So omega 0 is equal to 150 RPM. Before even moving on, my recommendation is convert this directly into radians per second. To do that, we need to multiply by 2 pi over 60, which is going to be 1 150 times 2 divided by 60 is 5. Yeah, okay. I don't know why that was so difficult in my head. So it's going to be 5 pi radians per second. Okay, I usually keep the pi if I don't have to change it, and if it's not already a big number, I keep the pi so it can be a bit more accurate when solving. Okay, up to you if you want to substitute the pi or not. It's fine. Okay, so this is the first step. From the very first sentence, I got that my omega 0 is in RPM. The first thing I do is convert it into radians per second. So the flywheel turns for how long? For 45 seconds. So our time is 45 seconds before the brake is applied to bring it to rest, meaning it is going to go to rest. يعني omega final is going to be equal to 0 radians per second. All right? With a deceleration of 0.5 radians per second squared. With a deceleration of, so this is our deceleration. So alpha is negative 0.5 radians per second squared. Now, before I even move on to read the question, you need to understand what this means. So the first part is it was constantly, these two parts are not the same, right? Initially, this was how much it was turning. It was turning for 45 seconds at a constant velocity, all right? This is at a constant velocity. Constant velocity معناته alpha here was equal to 0, all right? This is the first part. This is part 1, all right? So the first part is we had no alpha, we had a constant velocity, a constant angular velocity for 45 seconds, all right? Before the brake is applied to bring it to rest. So already it has moved for 40 seconds or 45 seconds at this speed. Then after that, the second phase now you could say is where our omega initial is the same, which is 5 pi radians per second. All right. The brake has been applied. يعني بعد ما 45 seconds مرة, the brake has been applied to bring it to rest, meaning now omega final is equal to 0 with a deceleration of 0.5 radians per second. All right. Again, it's a deceleration. Not it's negative. Now let's see what the question wants. Determine the total time. All right. So they want us to find total time. Let us first find the total time before we find anything else. So we already have the time for part 1. It was given to us. But let us find the time for part 2. Oops. So let me go grab my equations over here. All right. So what do we need to first find? We need to first find time. Actually, exactly the same as here. So here we have time is what we need to find. How do we find time? Using the first equation. So omega 0. And then omega 0 is 5 pi. Plus alpha, which is negative 0.5 radians per second squared, times the time which we need to find. Okay? So time is going to be equal to, now we just have to solve for time. So time is going to be equal to minus 5 pi divided by minus 0.5. All right? All I did was I took this to the other side. It becomes minus 5 pi. And then divided both sides by minus 0.5 so that this will cancel with the 0.5 under it. All right? This is just basic algebra. I'm not going to go through the steps all the time. So this is going to be equal to 10 pi. All right? Or in other words, it is 10 pi is 31.42 seconds. So for the first part, it was going for 45 seconds. For the second part, it was going for 31.42 seconds. So the total time will be total time. It's going to be equal to T1 plus T2. Let's call this T2. Let's call this T1. All right. So the first stage, which is this constant velocity stage, and then the second stage, which is the deceleration stage. So it's going to be 45 seconds plus 31.42 seconds. So it is going to be equal to 76.42 seconds. Okay, so now we found the first part, which was the total time. And now they're asking the total angular displacement of the wheel before and after the brake was applied. So we need it for phase before, which is phase 1, and plus phase 2. So phase 1 and phase 2. So how are we going to do this? Well, first, we're going to need to apply this equation or find the displacement using this equation. Since we have constant velocity for phase 1, all right? So again, we're going to do it for phase 1 and phase 2. Okay? Phase 1, we had omega 0. All right? Let me just say this is for theta or displacement. Okay? So the first phase, we had a constant velocity of omega 0, which was 5 pi radians per second. And we had our time t1, which is equal to 45 seconds. Okay? For a constant velocity, it's very simple. Theta is going to be equal to omega times time. That's it. لأن it's average omega, but since it's constant omega, it is the same. And if you remember from this equation, if you look at the last equation over here, it is, just so you guys understand what I did, it is omega final plus omega initial. But since omega is the same for both, معناته we have omega initial plus omega initial. This will become 2 omega initial over 2, which will cancel, and then we will have this final equation over here. All right? So this is what I basically did. So now we just have to plug in to find our displacement. Oops, sorry about that. Just a second. There we go. So now we just have to find our displacement. We have the values. So it's going to be 5 times time, which is 45, meaning displacement is equal to, what happened here? 1 second. بدي يخرف ال OneNote again. So we have 1 second. Let me just see what's wrong. Okay, should be fine now. So, okay, theta, like I said, is equal to omega, which is 5 pi, times the time, which is 45. Theta is going to be equal to 45 times 5 pi. It's 225 pi, or in other words, it is equal to, oops, times pi, 706.86 radians. All right, this is the first part. Now for the second part, it's after. We're talking, this was for theta, phase 1. Now let's talk about phase 2, when there was a deceleration. So when we had omega 0 was equal to 5 pi radians per second, we had acceleration or deceleration of minus, what was it? Minus 0.5 radians per second. And we had our last thing, which was final velocity, angular velocity, I should say, which was 0 radians per second. Okay? Now, we can apply the same equation that we did here because we have already found the time earlier, the time t2, which was 31.42 seconds. So we have found the time here to be 31.42 seconds from earlier, we can apply the same equation from here, this equation, to find our displacement, okay? Because we have our omega, we have our omega 0, and we have our time. So in other words, this is equal to omega is 0 plus omega 0 is 5 pi over 2 times the time, which is 31.42. So theta, our second displacement is, or our second phase displacement is equal to 5 divided by 2 times 31.42. You get 246.74 meters. Or sorry, we're talking about angular displacement, so it's radians. So the total distance now, total, or I should say total displacement, to be more accurate, angular displacement, is going to be equal to theta 1 plus theta 2. This is theta 2 for the second phase, and this is theta 1. All right? Again, this was time 1, and this is time 2. Okay, so that you can avoid confusions. So it's 706.86, 706.86 plus 246.74. So our total displacement is going to be equal to 953.6 radians. And that's how you would find your total total displacement after that. Okay? And that's pretty much it, how to solve. Again, you just have to know all these formulas and you'll be able to solve anything, and you need to make sure you know how to read this question. Let's do the final question. Also very straightforward. You just need to understand what you're doing. Let's do the final question. Why did we convert radians to radians per second? We have to always convert to radians per second to solve. We cannot solve using RPM in this case, because all our units is in seconds and in radians. And then when we're talking about acceleration, when we're talking about angular displacement, it's always in radians, all right? So we need to make sure that everything is in radians per second. Repeat this question. I will go over it very quickly again. All we did was we converted first radians per second. Then we had two phases. The first phase is the flywheel was turning at constant speed for 45 seconds. Then after that, this was the first phase, which was for 45 seconds. After that, there was the phase of deceleration, and بطأ الويل, يعني it became slower, until it reached rest. معناتها our final angular velocity was 0, and we had a deceleration of some sort. So here we had deceleration. The question wanted us to find the total time. The time 1 was given. Time 2, we can find it using this equation. We just applied to the equation and then found our second time. We added up the time for the first and second phase. Then the second part of the question wanted us to find the total angular displacement. Angular displacement, again, we use the exact same equations over here. All right. In the case of constant velocity, it's very simple. It is just speed times time is going to give you, or I should say velocity times time is equal to theta, or your angular displacement. And then we found it again using the exact same equation for the second phase, and then we added them up to find total displacement. It's very straightforward. All right. I will solve one more question, and then we'll take a break before we move on to the next topic. No worries. I will go through it very quickly. I'm not going to take too much time because it is exactly the same as what we have done so far. All right. But this is a good question because there is a small trick in it that most of you might find confusing. It's not that difficult at all. But if we look at it very quickly, so a rotor steam turbine revolving at 8,000 RPM. This is our first omega, which is 8,000 RPM. Convert it into, this is omega 0, convert it into radians per second. So what do? We multiply by 2 pi over 60. This is going to give us 8,000 divided by 60 times 2. It's going to give us 800 over 3 pi, whatever the value of that is. And then it slows down, so we know there's a deceleration process to 2000 RPM. So W, or final angular velocity, is equal to 2000 RPM. Again, we are going to multiply by 2 pi over 60 to convert into radians per second. So this is in radians per second. So 2000 times 2 pi divided by 60 is going to be 200 over 3 pi. All right? Radians per second. Okay? So what does the question want us to do now? Oh, and then we also have in 15.7 seconds. So we have the time, which is 15.7 seconds. So from this, we already have 3 unknowns. When we have 3 unknowns, we can solve basically for anything using these set of equations. Okay? So let's first see what they want us to find. Determine angular deceleration. So that's the first part. They want us to find angular deceleration. In other words, we need to find alpha. All right? So part A, we need to find alpha. We can use the first equation again. Now we have the time, but we do not have alpha. So omega, again, make sure everything is in radians per second. So it is going to be final omega, which is 200 over 3, is equal to initial, which is 800 over 3. This is pi, of course. There's a pi here and a pi here. Obviously, you guys can put the actual numbers here instead of dealing with pi. I just prefer usually keeping it this way to be more accurate. Times alpha, which we need to find, times the time, which is 15.7. And now we can just solve for alpha here. فبيستوي 200 pi over 3 minus 800 pi over 3. And then is equal to alpha and into 15.7. So we're going to also divide both sides by 15.7 directly over here and over here. And we'll plug it all into the calculator. These will cancel. And we find that our alpha is going to be equal to 200 over 3 minus 800 over 3 times pi divided by 15.7. Obviously, we're going to get a negative value of negative 40.02 radians per second squared. The reason it is negative is because we are slowing down. We are going from a higher RPM to a lower RPM. This is why the value is negative, which makes sense because it also says slowing down. And now it says the number of revolutions made by the rotor in that time. What does this mean, number of revolutions? When they're talking about, they're not saying revolutions per minute. They are saying, if we look back at the question, they're talking about the number of only revolutions. Number of revolutions meaning we're talking about theta. So usually we talk about theta either in revolutions or in radians or in degrees. All right. So this is the way you talk about our angular displacement. It's either how many revolutions, how many radians, or how many degrees. Okay. So now what do we need to find? We need to first find our theta in radians per second, and then we can convert it into revolutions, or sorry, in radians, and then we can convert it into revolutions. So we can use any equation we want from here. We can either use the second one, because we have omega and alpha. We can use the third one, because we have all of this. We can use the last one, because we have, you can use basically any one of these. I usually prefer using the average one at the bottom, but again, it really does not matter which one you're going to use. So if we apply this equation now, this is going to be equal to, all right, omega plus omega 0 over 2. Our omega is 200 pi over 3 plus 800 pi over 3 all over 2. Again, I keep it in this form just to be a bit more accurate. The time is 15.7 seconds as given in the question. All right. And now we have found our theta to be, we plug all of this into the calculator. Divide by 2 times 15.7. I get 8,220.5 radians per second. Remember, now we want to go from radians per second to revolutions. What do we have to do? We have to divide by 2 pi. So it's going to be theta is equal to 8220.5 divided by 2 pi revolutions. Or in other words, if we just do this division very quickly, we get 1308.33 revolutions. All right. So in this amount of time, this steam turbine, the rotor of the steam turbine, has rotated or I should say had this many revolutions, or 1308.3 revolutions over 45 or over 15.7 seconds at these RPMs. Okay. Let's take a short break for now. We have finished all of worksheet 1. We'll be back at, let's round up. So let's make it until 8:20. All right, so back at 8:20, and then we will start solving worksheet 2 with the new concept. All right. If you have questions, feel free to ask. I'm not going to start the new concepts, but if you have any questions, you can ask. I'll be around. How 200 pi over 3 is final. So a rotor of a steam turbine revolving at 8000 RPM slows down. So معناته في البداية كان على 8000. Then it is slowing down. معناته بعدين بطأ السرعة ووصل لسرعته ل 2000. That's why this will be our first value, which is the initial value. Then the 2000 is our final value. تمام? Meaning that this is our final value, and then we converted it from RPM into radians per second, simply by multiplying by 2 pi over 60. This is why 200 pi over 3 is final. All right? Again, if you have any questions, feel free to ask. I'll be around. All right, let us continue. So now we talked about angular motion in general, about omega, alpha, and all of that. Now, what about if we are talking about angular motion and in comparison with linear motion? Yani when you have both happening in the same time. More specifically, in your case, what I have seen is you will usually get a pulley of some sort. All right. And you're going to have a load extended from it at the bottom with a specific mass. Okay. Ignore the arrow. And then, so you're going to have a specific mass attached to a pulley, and you're either going to try to pull up the mass, or the mass is falling down, or something is happening. There's going to be rotation in some case. Okay. So obviously this pulley is going to have a specific diameter or radius, a radius r, and it is going to have a mass. We're going to call mass of D. Usually they call it drum. All right, a drum or a pulley, and I'm going to call it MD. And here, this is going to be our load, which I am just going to call the mass of the load as ML. Before we talk about the drum, let's talk about the mass a little bit. So we know from basic mechanics, this is going to have a weight force down here, right? And then there's going to be, this is going to be W, which is equal to mass L times gravity. Obviously, it is always downwards. And then let's say if, for example, this mass is being pulled up, it is going to have an acceleration upwards. All right. فمعناتها في acceleration upwards, meaning that it is trying to overcome the mass due to the weight, and it is trying to overcome the inertia of this, known as F equal ma, which is the force due to the mass of acceleration of the mass. Pretty sure you all know what F equal ma is by now. And to be more specific, this is F equal mLa. All right, the mass of the load times the acceleration. All right, so if we're assuming acceleration is upward, this force due to the mass is going to be trying to push it back. This is the inertial force, basically known as the reaction force of this acceleration going up due to the pulley. All right, yani if this pulley is rotating to the left, or I should say counterclockwise, it is going to be pulling this mass up, and this is going to be acting in the opposite direction because it is the mass of the load itself that is trying to go down or trying to resist this acceleration. Each action has an equal and opposite reaction. Another way you can draw this is if you have this going down, this going up, this meaning the tension in the rope going down, this is the tension of the rope going up. All right, so they're opposite, equal, and opposite reactions. So this is when we're talking about the pulley, all right, or sorry, the load. What about when we look at the pulley? So for the pulley, we're going to have a rotation. In this case, our torque, which is the rotation of it, basically, our torque is going to be in this direction. So, yani the pulley has to be powered into a counterclockwise direction so that this acceleration will occur and the load is going upwards. Tamam? So for this specific case, the torque has to be counterclockwise. When you have a torque that is going counterclockwise, you're going to have the friction of the pulley, and it's installed in the middle over here, okay? So this is installed in the middle somewhere, and it is rotating around that point. So you're going to have a friction that is obviously opposite to where the torque is going. So the frictional torque, I should say, okay, is going to be on the opposite direction of where the torque is going. That is the first thing, okay? The other thing is, now we have an angular acceleration. What is the angular acceleration? Angular acceleration is going to be in the direction of, so this is alpha. Angular acceleration is in the direction of where the thing is rotating, right? But similar to the case here, where we are having a mass, the acceleration being opposite to the mass, because this is the inertial force of it. Inertial force meaning يعني it's resistance to the motion of where it is going. The same thing is going to happen here. We are going to have a torque, or I should say an inertial moment known as I alpha, that is acting opposite to where alpha is. يعني basically this alpha or this torque needs to overcome this inertial alpha over here, depending on what the rotational acceleration of it is. All right. So again, we have the torque friction. This friction is due to the pulley installation, يعني whatever it is. Then you have I alpha, where I is inertia. Okay, and I'll talk about that in a bit. And alpha is our angular acceleration, which you already know. Angular acceleration. TF is our frictional torque. And we have T اللي هو the actual torque itself, I should say the accelerational torque if you want, or the actual torque that is being applied. Let's call it applied torque. Okay, applied torque اللي هو بما معناه power that is generated in this motor or whatever to make it rotate counterclockwise. And this is the case all the time, all right? So you'll always have acceleration and torque in the direction, and then the frictional and the inertial response in the other opposite direction. And remember, torque, again, we can use our sigma moment for torque, similar to what we did before. This inertia is also known as second moment of inertia, because there are two types of inertia. So this is second moment of inertia. All right. No need to understand fully the namings and all of that and where everything comes from. What you need to know is just the directions. When you have a torque going this way, that means acceleration is going to be going upwards. إذا هذا قاعد يدور بهالاتجاه معناته our acceleration is going upwards. So once we have an upwards acceleration, we know the direction of the torque. We will also know the direction of our alpha, because this is where it's accelerating. And the frictional is always going to be opposite to the torque. And also the I alpha is going to be opposite to torque. All right. So before I talk about inertia, I'll leave that to last. Let's talk about the alpha. Remember the equation that I said early on, that alpha is equal to, or actually how I wrote it was, I said acceleration A is equal to alpha, or R alpha, all right? This acceleration over here, the linear acceleration, is equal to the radius times alpha. So we can simply find, if we are given acceleration, we can find that alpha is simply equal to the acceleration over the radius. All right. So we can find the value for alpha no matter what the case, as long as we have the radius, which is most of the time given, and the acceleration, which is most of the time either given or needs to be found. All right. So this is a relation that you need to know. One more thing, inertia is usually given in the question. However, in some cases, they talk about another value known as K, which is the radius of gyration. Radius of gyration, just so you guys understand what it is, radius of gyration is an invisible radius, and then a مو an actual radius that you have, but it is an estimated radius, you can say, of any type of body that is rotating. All right, so let's say that this is rotating over here. Okay, if you want to measure the radius of this body's radius is known as K, which is basically an average radius of the shape of this body. And then again, you don't need to know all the details about this, okay? But this is just the radius of this average body, and the reason you find this is to find your moment of inertia. How do you do that? So let's say this body has a mass m. In this case, usually we talk about the body of the drum, so it's md, all right? to find our I in this case, I will be equal to md times k squared. All right. No need to get confused too much about radius of gyration. All you need to know is that you could, when this is given, this is to find the inertial inertial moment or second moment of inertia. And remember the units here. Inertial moment is going to be in kilograms meters squared. Mass is obviously in kilograms, and K is in meters, right? This K is in meters, which will be squared on the outside, all right? The square over here. كل اللي لازم تعرفونه إن if you see radius of gyration and mass of the drum, you multiply this with the radius squared, so you can find your inertia, and then you can solve. So when I'm saying solve for what exactly? If we look at this, if we look at this setup over here, so let's say we have a total force over here that is called E. All right, let's call this force E, and then which is the tension basically in the cable. If we look at the bottom part, if we're just analyzing the bottom part now, and then I'm just going to redraw it here. So we have the weight W, which is equal to M times G, ML times G, because this is the mass of load, the mass of the load, and we have friction in this case where acceleration is upward, right? In this case, we have the force of inertia, which is mass times acceleration, acting in the opposite direction, which is MLA. And then we have the tension in the rope, which we called E. Okay? This tension in the rope, which is called E. If we apply our sigma Fy equation, sigma Fy equal 0, that means our E is minus F minus W is equal to 0. In other words, our E is equal to F plus W. In other words, our E is equal to, our F is ML acceleration plus ML gravity. So you can take ML common if you like to keep your equation as this, acceleration plus gravity. Okay? This is the total force, or the total force, I should say tension force in the wire or the pulley or the chain or whatever, okay? Due to the mass of this load and due to the acceleration of this load as well. So this is our E when we are looking at it from the perspective of the body. Now let's look at this pulley over here, or this drum in this case, okay? So when we're looking at the drum, this is what it looks like by itself. We have already analyzed the bottom part. We have analyzed the bottom part to be simply a tension force that is going into this direction from the load that we named E. Here in this case, we are talking about rotations. We are talking about rotations about what? About the origin, I'll call O, all right? This point of origin, which is the center of the circle. Tamam? This origin, we are going to take the moment about it. So sigma moment about O is going to be equal to 0. And now we need to identify our positive and negative directions and all of that. Let's say that we take counterclockwise as positive. All right, it doesn't matter which direction you take as positive. You take one of them as positive and you solve. So let's say we're taking counterclockwise as positive. So remember, this is just acceleration, okay? This isn't an actual moment or torque. This is just acceleration. This is the actual torque, which is T. So we're going to have T, positive T, because it is counterclockwise, minus TF, minus I alpha. And we have one more additional thing, which is the moment due to E. How do you find moment? Again, if you remember, perpendicular distance, this is how you find moment. You multiply, this is a force, right? Remember that this E is in newtons. This is a force, okay? So this multiplied by the radius. In other words, it is going to be E times R. to find the moment about point O. And what is the direction? So this is going into this direction, which is the clockwise direction, okay? Meaning it is a negative value as well, which is equal to 0. And remember, E is basically what we have already assigned over here, which is the mass times A plus G, which we have derived from our equation for a free body diagram for the load. So finally, we have an equation where T is going to be equal to, if we take everything to the other side, it is the friction, torque, plus I alpha, plus, let us substitute for E, ml A plus G, mass of the load A plus G, times the radius, so we also have radius, which is equal to, that's it, which is all equal to the torque. And remember, torsional friction, this is going to be given to you in the question. I, you can find easily, so if we want to break this down a bit more, I is equal to md times k squared, and alpha is simply equal to A over R from the equations that we have derived earlier. I is equal to mdk squared, and alpha is equal to A over R. And now you're going to have all the known values that you are needing, you need to be able to solve for this question. Let us actually do this in practice. Let me see, how acceleration is upward. This is just an assumption that I made. If it was decelerating, alpha will be in the opposite direction of motion. Yes, if it was decelerating, which we will see an example as well, if it was decelerating, everything is going to change. Your F now is going to be going upwards because the acceleration is going downwards. However, weight will stay downwards. And we're going to see an example about that. And here your rotation is going to be clockwise, not counterclockwise. And we're going to be looking at examples. It's better to do it with numbers. This is just the theory behind it. Let's solve the first question. Where's the worksheet? Over here. Actually, I'll skip the first question. Let's solve the second question because we are solving for the exact same thing, but it has also additional information that we will be able to solve. All right. The first one is very similar to this. If anything, it's much easier than this because friction is also neglected. So you don't have, so basically your TF is 0. But let's start with the second question. Okay. So read the question very carefully. A mine cage, this is basically your load. All right. This is your load. Let me keep the load color as orange. All right. A mine cage of mass 4,000 kilograms. So our M load is equal to 4,000 kilograms. Is to be raised with an acceleration. This is our acceleration. Let me keep actually acceleration in purple. All right. With an acceleration of 1.5 meters per second squared. This is our A value, which is 1.5 meters per second squared. And notice it says raised, meaning that the acceleration is going upwards. All right, or in other words, we can assume as positive. Okay. Using a hoist drum of 1.5 millimeter diameter. So we know that our diameter is 1.5 millimeter or meter, which first thing you're going to do is convert this into the radius, which is half of the diameter. So it's 0.75 meters because we do not benefit from diameter. We want it to be in meters. Okay. So this is the first thing. The drum's mass is 750 kilograms. So M drum is 750 kilograms. And this is the mass of the drum. And its radius of gyration is 600 millimeters, which is our K. K is 600 millimeters. Again, instantly you are going to be converting this into meters by dividing by 1,000 and you will get 0.6 meters. Make sure you're always making sure that you're in your standard units. Do not keep anything in revolutions per minute or in millimeters or in kilonewtons, always change them to the standard units, all right? The effect of bearing friction is equivalent. So the bearing friction, this is what I was talking about. This is your frictional torque, is equivalent. So bearing friction is equivalent to a couple of 3 kilonewton meter. A couple meaning a moment or a torque. All right, this is all they mean by a couple. So TF is equal to 3 kilonewton meter, which is equal to 3000 Newton meter. Again, converted from kilo into Newton meter. So far we have TF. We have our mass for the load and the mass for the drum. We have our acceleration. We have our radius. And we have our radius of gyration and the mass of the drum, which I already said. First question says, find the torque required on the drum. Okay, again, if we're going to be looking at this this cutout, let me just take it down here because it's the exact same example that we are dealing with here. Okay, so this is what we are dealing with. Okay, so this is our drum. Now we know that we have an acceleration over here. Our acceleration A is equal to 1.5 meters per second squared. Our radius, which we found, is 0.75 meters. Our mass for the drum, all right, we have already found it to be 750 kilograms. Our mass of L, we have already given 4,000 kilograms. And our W, basically we can find it. Remember that G is 9.81. And we have this acceleration already given to us. We have the value of it. I'm just going to keep it in this color. And we need to find our torque. So remember, we are going to be deriving this equation basically every time, all right? But just to save some time, I have already done the derivation and showed you how to do it. I'm just going to use this equation directly over here, okay? So we are going to do the sigma moment. Sigma moment, actually, let me go through it so you understand what I'm doing one more time. So I'm going to do the sigma moment at this point in the middle, all right? Before that, actually, let us do our sigma Fy for the load at the bottom. So sigma Fy equals 0. Again, our force is going downward. Or first, let's look at our E. Our E is upwards, so it's positive. Minus our force F, which is downwards because of inertia. So it is MLA. All right, this is just our force F. Minus M load G. This is our force, the weight force W, all right, because they're both pointing downwards because we have an acceleration going upwards, equal to 0. In other words, our E is going to be equal to MLA plus G. If I just take them to the other side and take ML common. If you notice here, we already have the mass of the load as 4,000 kilograms, and we have our acceleration, right? So our acceleration is the purple acceleration A that we have, and we know G, and we know ML, so we can simply just substitute the values for this and find it directly. ML is 4,000 kilograms times A, which is the acceleration we have, which is 1.5 meters per second, plus G, which is 9.81 or 9.8, or whatever the assumption you want to take for G. Our E is going to be equal to, if we put all of this into the calculator, so 1.5 plus 9.81 times 4,000 is 45240 newtons. All right, remember, E is simply just a force. Okay, so we have found our E force. So we are done now with the bottom part. We have already done our analysis here. الحين we are looking at our rotational or torque. زين, our rotational or angular motion and our torque. يعني now we are going to apply sigma moment about O is equal to 0. So if I just bring this part again down here. So So we're only looking at the circular part now, okay? So again, our acceleration is going into this way because we know that acceleration here is going upwards. بالمنطق إذا هذا قاعد يروح فوق معناتها هذا لازم يدور counter clockwise. Okay? Since this is going in counterclockwise direction, friction is going to be opposing it. I alpha is also going to be opposing it. And that's pretty much it. And the torque is in that direction. And we know that we have our force E down here, which we have already calculated, by the way, up here. 45240. But for simplicity for now, I'll keep it as E. All right. Before finding the moment, all right, what do we need to find? We need to find our I value. So I is equal to mdk squared, which is equal to md was the mass of the drum, and k was the radius of gyration that we have found here. So it's 750 times 0.6. So 750 times 0.6 squared. Okay, so our I value is going to be equal to 0.6 squared times 750. That's 270 kilograms meters squared. Tamam? So we find our I value. Now we are going to find our alpha. Again, alpha is simply equal to acceleration, which we have, I'm going to keep in purple, over the radius r, which is equal to, we know our A is equal to 1.5 meters per second, and our radius we found is 0.75. So 1.5 over 0.75, which is going to be alpha is equal to 1.5 divided by 0.7. Oh, it's 2. All right, so it's 2 radians per second squared because we're talking about angular acceleration. Tamam? Now, we have found everything that we needed to find. We have also been given TF, the value for it. Now we can just find our moment about 0. All right, how do we do that? Look at directions. Again, I will assume counterclockwise as positive. This is point O. The torque T is equal to, or sorry, torque positive. Then we are going to say minus TF because it's in the opposite direction, minus I alpha, which is in the opposite direction. And then we have our last thing, which is our E. Our E is pointing downwards. All right. I'll make this shorter. Our E is in the downwards direction. So معناته it is causing a a clockwise moment. All right. So it's causing a clockwise moment, meaning it is going to also be minus E, which is equal to 0. So if we plug in the numbers now, or first let's simplify this equation, put TF on the other side, because we need to solve for T anyways. My plus I alpha plus E. So I just took everything to the other side. And now we can plug in all the values that we have found for all these unknown variables. So TF was given in the question, which is 3000 Newton meters. So the torque is going to be equal to 3000 Newton meters plus I, which we have found earlier here, 270 kilogram meters squared. So 270 times alpha, which is radians, 2 radians per second squared. So 2 plus E, which we have found earlier as well. All right. This is the value for E, which was 245240. 45240. Yes. All right. 45240. I forgot one more thing. Their radius. This is E times R because this is a force. And then we need to multiply the force by the radius to get it in Newton meters or to get the moment about it. The force times the perpendicular radius. So this is E times R. So 45,240 times the radius, which is 0.75. And now we can simply just add up all these values to find the torque value. Bringing out the calculator, 3000 plus 270 times 2 plus 45240 times 0.75. It's going to give me 37470 Newton meter, or you can say this as 37.47 kilo Newton meter. All right. As a final answer, you can keep it in this form. Nothing wrong with that, unless the question specifies in which units. Okay. So this was how it was solved for part A. Let's see if any questions about part A. Is it possible to raise the load and decelerate? It is not. Technically, yes. But in the questions, I haven't seen anything like that. Yani, you mean if the load is going up, because it will never decelerate unless it already is starting with a specific speed. All right. And we'll see an example of that. I think it's here actually. Yeah, we will look at this in part B now. When drawing the free body, how to know the directions of E? Very easy. The directions of E is going to be upwards for the bottom part. It's in tension. It's pulling the bottom part. And for the upper part, it's pulling it down. It's the opposite case. All right. If a load is down here, when you're pulling it, the force is going upwards in the شو يعني here, when you have a load, if you're trying to pull it, your force is upwards because you're trying to take it up. All right. In this case, from this point of view, from the drum, there is a tension or something pulling it down. So it's going to be in the opposite direction. These E is the same, which is equal and opposite direction. Newton's third law. All right. What if it's lowering? We're going to see an example of that in a bit. Let me solve part B. If the driving torque is stopped when the velocity is 6 meters per second. So here, they're saying that this torque stopped. So basically, we reached a velocity of 6 meters per second, and the cage begins to decelerate at a rate of 9.64 meters per second squared. Meaning, now we have an acceleration, okay? We have an acceleration upward, but now it is slowing down upwards. معناته it is still going up, but it is moving at a slower rate. يعني قاعدين يخففون سرعته. And how far will it travel before coming to rest? So let's look at the numbers that we have here, okay? So the first thing is we have V0, which is 6 meters per second, all right? Because this is our initial point, right? Before the cage beginning to decelerate, the driving torque is stopped when the velocity is 6 meters per second. So initially, it's at 6 meters per second when we start this phase of action, you could say. All right? The cage begins to decelerate. Decelerate meaning this is our acceleration now. This is our new acceleration at a rate of 9.64 meters per second. So it's a negative acceleration. How far will it, let me keep this actually in a different color. Since I'm using purple for acceleration, let's keep it that way. Let's use initial as red. And let's use final as blue. So how far will it travel before coming to rest? All right. We are talking now about linear motion. We're not talking about angular motion. We have velocity in meters per second. We have deceleration, which is acceleration in meters per second squared. And how far will it travel, which is displacement S in meters, before coming to rest, meaning this is our final velocity of 0. So, let me just plug down the numbers. نروح الوركشيت. Okay. So the question was saying, so this is for part B now. We have an initial velocity of V0 or U, basically. U is equal to 6 meters per second squared. Okay. Let me actually do something better so that we can see where I'm getting these numbers from. So this is what the question was saying. If the driving torque is stopped with a velocity, this is the first velocity, the initial velocity, as I said earlier, the cage begins to decelerate, meaning the acceleration الحين negative. So our A is equal to minus 9.64 meters per second squared. How far will it travel before coming to rest? And this is our velocity, final velocity, which is 0 meters per second squared. Let's go all the way back to the very beginning of this lesson where we had these equations. All right. So we're going to have to select an equation from here that has these three values, which is acceleration, initial velocity, and final velocity. Okay. So we're going to have to select one of these equations. Okay. What do we have? We have acceleration. So something with acceleration. Unfortunately, here I swapped the colors, but it's fine. We want this is our acceleration, our u, which is here, and our v, which is here. And what are we trying to find? The distance covered, so our s, which is right here. So we're going to be using this equation over here to find our s value. So in other words, we are going to say v squared, which is 0 squared, minus u squared, which is 6 squared, is equal to 2 times the acceleration, which is negative 9.64, times s, which is what we are trying to find out. Again, this is our v, this is our u, and this is our acceleration a. All right? So now we just solve for s. We're just going to divide both sides with this over here. So it's going to be s is equal to minus 36, which is 6 squared, over 2 times minus 9.64. Therefore, our s value is equal to minus 36 over 2 into negative 9.64, which is 1.87 meters covered. So this is how much it has covered, or how far it has traveled after the acceleration has stopped, يعني after the torque has stopped. In the solution manual, I noticed something. What they did was they actually combined the total distance from the very beginning to the very end. I don't know why they did that. In this question, it very clearly says how far will it travel before coming to rest when the cage begins to decelerate. So معناته we are talking about only the phase where it is decelerating. All right. Either way, it is very clear how to apply it. You just have to know your linear equations, just like you know your angular equations. You need to understand what is your initial and your final, and you apply it. Let's do one final question, which is in the case of the deceleration or free falling, actually. All right. So let's look at this question. I'm going to try to go through it very quickly as time is running out. So a hoist drum has a mass of 360 kilograms. The drum, so the mass of the drum is 360 kilograms. All right. Radius of gyration K is equal to 600 millimeters, or in other words, 0.6 meters. Then remember that these two values will give you your I, which is equal to mdk squared. That is the only reason you would use these two values. The mass of the drum and the radius of gyration is just to find the value of I using this equation. So it's equal to 360 times 0.6 squared. So I is going to be equal to 360 times 0.6 squared, which is 129.6 kilogram meter squared. All right. So we are done with these two values. That's the only reason we need them, is to find our I value. Let's keep on reading. The drum diameter is 750 millimeters. So 750 millimeter, or it is 0.75 meters. معناته our radius is just half the diameter, which is 0.375 meters. Okay, once you get your diameter, instantly find out your radius so you can find out all the other values. A mass of 1,000 kilogram hangs from a light cable. So now our M load is 1,000 kilograms. Okay. From the light cable wrapped around the drum, and this is the very important part, allowed to fall freely. Allowed to fall freely. Why is this important? When they say free falling, this implies that your torque is equal to 0. That's what free falling means. معناته the hoist is not rotating, or there is nothing forcing it to move. زين. If the friction at the bearings is this value, 2.7 kilonewton meter, so T friction is equal to 2.7 kilonewton meter, or in other words, 2,700 Newton meter. All right. Calculate the runaway speed of the load after falling 2 seconds from rest. We will look at the calculate the runaway speed first, but if you notice here, to find any speed or anything like that, we first need to determine our acceleration. So let me bring down this drawing so I don't have to redraw it again. Okay, now we have a different case. Here, the case is we are no longer pulling the load upwards. Okay, we are no longer pulling the load upwards. Now the drum, now our load, the acceleration is actually going downwards, and we do not have the value for acceleration. So since the acceleration is going downwards, that means our F now is going upwards. It is acting in the opposite of where the acceleration is. It is the inertial force due to acceleration. زين؟ معناته هني we do not have torque anymore. Torque is 0. So there is rotation, but without a forced torque. All right, يعني there is a rotation, but this rotation is only due to your E in the cable. Okay, meaning that this pulley is going to rotate, and you are going to have a friction, and you're going to have an acceleration, but now your acceleration is in the opposite direction. Your alpha is going to be in this way. Okay, since your alpha is in this way, your I alpha is going to be in the opposite direction as well. So I alpha now is in the opposite direction of alpha. And since this is the motion rotation as well, your friction is always it's always going to be in the same direction as your inertia, by the way. So you can keep that as a note. So your friction is also going to be in the opposite direction because this is now going downwards. Okay? Now, here, if you notice, our friction force or the inertial force now has changed. So now when we want to do our sigma Fy equals 0, our tension is still in the same direction. Our E is still up. There's still tension upwards in the wire. So E is positive, plus F minus W is equal to 0, because now F is in the upwards direction. معناته E plus MLA minus MLG is equal to 0. معناته E is equal to MLG minus MLA. Because if we take this to the other side, it becomes negative, and if we take this to the other side, it becomes positive. In other words, our E now is equal to MLG minus A. Okay, this is the very first thing. So now we did our analysis. Now you notice we have a negative because the direction of this force changed, and the weight will always be downwards no matter what. All right. Now, let us look at the drum. Okay, let's look at just the drum. If we're looking just at the drum here, now we are going to look at the moment about O, where this is point O. Counterclockwise is positive, and it's going to be equal to 0. So now we have our counterclockwise positive means I alpha is positive, plus the friction, which is positive, right? Because they're both in a clockwise, minus E, because E now, if you notice, did not change. It's in the same direction. It is going into a clockwise direction. So it is a negative value times, obviously, the radius, which is no longer 0.75. It is 0.375 meters. All right. Same thing here. It is 0.375 meters. We found it earlier. Okay. So now, when we are doing our moment equation, this is how it's going to be, and it will be equal to 0. All right? So what's the point of all of this? What am I trying to solve for? We are trying to find our acceleration. Remember, we have our acceleration now downwards. This is our acceleration. We have found our I, but our alpha, we didn't find it, but we can find it in terms of acceleration, which is alpha is equal to acceleration over R. All right? So now we can plug in all our values to solve for our acceleration, as it is our only unknown variable. So we found our I early on. Our I was 129.6, 129.6 times alpha, which is A over the radius, which is 0.375, plus the frictional force, which was given to us as 2,700 Newton meters, minus E. What is E? Again, let us just plug in the values here for E. E is M load. M load is 1,000 kilograms. So it's 1,000 times 9.81 minus A. Remember, this is our acceleration A, that is the unknown that we are trying to find. So it's going to be minus E, which is 1,000 times, actually, let me simplify it from the beginning here so that I can just write it in simpler terms here. إذا وزعنا بيكون عندنا 9810 minus 1000 A. Okay, so over here, we are going to have the same thing, which is our E value, which is 9,810 minus 1000 A. All right, times the radius that we have, which is 0.375 meters. All right, and this is all equal to 0. Now we have one variable, which is acceleration, and we're going to solve for it. So 129.6 divided by 0.375, that is 345.6 A plus 2,700 minus, and نوزع 0.375 inside, so 0.375 times 9810, it's going to be minus 3678.75. Minus and minus becomes plus. 1,000 times 0.375 is 375 A equal 0. Now we group our A's together and take the constant to the other side. So we're just going to group up these two. Okay, group this up with this. And we're going to be grouping up these two numbers as the constants, and then we'll take them to the other side. That's all I'm going to be doing. So 375 plus 345.6, that is going to be 720.6 A is equal to 2,700 minus 3678.75 is going to give us negative 978. When we take it to the other side, it's going to become a positive value, so positive 978.75. Therefore, our acceleration is equal to 978.75 divided by 720.6, which is 1.358 meters per second squared. So we have found our acceleration, all right? However, this isn't what the question asked. What did the question want? Now it was saying calculate the runaway speed, meaning your final speed, right? This basically means the final speed of the load after falling for 2 seconds, which is the time, from rest, which is your initial velocity. All right? So in other words, this means our U is equal to 0. We're trying to find V. And our time is equal to 2 seconds. And these, we're going to use what we have found, the acceleration here, to apply and find our V value. All right. So the basic equation is V is equal to V is equal to U plus AT. All right, we have our U, we have our A, we have our T, we just need to find V. So it is equal to 0 plus A, which is the value that we have found, 1.358, times time, which is 2 seconds. Therefore, T is going to be, or sorry, V is going to be equal to this times 2, which is 2.72 meters per second. And this is your final answer. So just a very quick recap in general. When you have the directions in the opposite way, you notice that your sigma Fy will change and the direction of your torque and rotations will also change. Unfortunately, I did want to solve all the questions, but I was taking a bit too much time just to make sure that the concept is clear. Inshallah, if there is more time in next sessions, or if I manage to get some extra session, I'll try to solve